Hi everyone, let's continue our discussion about big O. Okay, so let's do a very quick review. In the last lecture, we talk about the asymptotic performance analysis. And this means we are interested in the running time and especially when the problem size is large. If you are using the sorting algorithm as example, if you have only a few dozens or a few hundreds of the values to sort, you don't worry about the time spent in this algorithm too much. You just use whatever sorting algorithm, you can get work done. Okay, and then if the data set is large and like if you have 1 million, and then we have to have some serious discussion about the time complexities or the algorithm performance. And when we are discussing the algorithm performance, and remember we are using the RAM model, and if you forget what is RAM model, you may want to refer back to the computer architecture course. You should have this concept covered here. The RAM model may not be true because there are a few assumptions that are not even true on your computers. And for example, all memories are equally expensive. That's not true. If you were in computer architecture or operating system course, and you may know there is also a memory called cache, and the cache are smaller and faster than our main memories. But when we are discussing about the algorithm complexities, and we just assume that all the memories are equally expensive, and then we assume that there's no concurrent operations, and if you have multiple cores in your processor, and actually you do have that, and for all the reasonable instructions, and they take the same time, and this may not be true. And for the constant word size, it may not be true either, because as we know, a integer versus a float, the space they take in the memory, they are not the same. Why do we assume this if they're not true? Because we want to simplify the scenario a little bit while we are talking about the time complexity. We are putting the algorithm analysis in an easier scenario where we discuss the time complexity. Okay, as I said in the last lecture, if we are using Qualcomm computing, and then everything will be changed. Okay. For the running time, remember when we are doing the analyze the running time, and we are not using a stopwatch to time how long it runs. Or if you want to do it old style, you can do the stand timer. We are not doing this. Okay, and our approach will be, we want to count how many primitive steps have been executed from the beginning of the algorithm all the way down to the program is finished. Okay, and then as you may feel, if we execute more lines or more primitive steps to finish a whole algorithm, and then the running time will be longer. Okay, and another thing is, we usually analyze the worst case and the average cases. It's not common that we analyze the best cases. Okay, and we talk about the insertion sort. And for the insertion sort, long story short, we start from a random list. We don't know whether the values are sorted or not. And then what's our thinking? Our thinking is we want to start from the first value, and that value itself is sorted, of course, so that's good. And then we want to expand the sorted portion to the first two values. So for the second value, we just expand that, so we have to find the right place for the second value. And after that, the first two values are sorted. And after that, we want to expand the sorted portion again to include the third value. And as we include the third value, and then we may have to shift the values to one side, and then we want to insert the new value in to the sorted portion. So our thinking is we keep on expand our sorted portion, and eventually, if we expand the sorted portion to all the values in the list, and then all the values are sorted, right? Okay, and for the insertion sort, Well, here are some of the questions I leave to you. Well, if the values are pre-sorted from low to high, what is going to happen? Okay, so let me use the values I used in the last lecture again. So how about we have those values 1, 3, 5, and 6. Okay, they are pre-sorted from low to high. Okay, and then in the very first round, say if we only consider 1 as a sorted portion, nothing to do. Okay, and then we expand, we want to include 3 into the sorted portion as well. So if we have the 3, we want to do a check, but 3 is at the right place. So we expand 3, but we don't have to make the place for 3. Why? Because 3 is already at the right place, right? And then if we want to expand again, how about we also include 5? When we include 5, okay, so we want to check if 5 is at the right place, and the answer is yes, 5 is at the right place. So we do a check for 5. However, we don't have to make the place for 5 because 5 is at the right place. And we include the 6 into the sorted portion. Again, we don't have to do anything extra. Why? Because for each of the new value we are about to add into a sorted portion, it turns out that it is already at the right place. Okay, so for the pre-sorted input from low to high, what is that? That's the best case. Okay, and how about the opposite? 6, 5, and then 3 and 1. Okay, 6, 5, 3, and 1. And what is going to happen? To begin with, we only have 6. When we only have 6, okay, not bad. It is sorted because there's the only value. But if we are expanding the sorted portion to include 5, what is going to happen? So we have to move 6 to the right side so that it makes a place for 5, because 5 has to be shifted to the left side. Okay, my left side, okay, or your right side. Okay, so well, that is the first two values, and then we have already to do a shift. So 5 and then 6, and what's next? Say the next value I want to include is 3. So we want to expand the sorted portion, and then we want to include 3. And what is going to happen? So for that 3, it turns out that 3 has to be, well, 6 has to move to the right side, 5 has to be moved to the right side, so eventually, so that we can make the place for 3. So how many shifts do we have to do? We have to do 2 shifts so that 3 can be put into the right place. Okay? And then eventually we include 1. So 1, if we want to include 1 into the sorted portion, what is going to happen? So 6 shifts to the right side, 5 shifts to the right side, 3 shifts to the right side, so eventually we will have the space for 1. Okay, so how many shifts? There are 3 shifts because all those 3 values have to be shifted before we can really put the 1 at the right place. So for the second part, pre-sorted input high to low. Is that the best case or the worst case? That's the worst case, right? So, okay, another question is, if we increase the input size, how many more steps does this algorithm do? Okay, so what's your answer? Your answer is, it depends on what case we are in. Say, if we are at the best case. For the best case, well, we just do checks. We don't shift any values, right? So if we double the size, for example, and then we just need to double the number of the checks, but we don't have to shift any values. So for the best case, well, doubling the input size is not terrible. But how about the worst case? So for the worst case, and then we are going to have a lot more shifts to do. So you may have a feeling that if we are in the worst case and then we double the input size, and it's not so good. Okay, so well then let's try to let's try to do a very quick review of the insertion sort. We have gone through this before, so I'm going to be a little bit faster this time. Okay, so we started from where? We started from I equals 2 because, well, for the first value at the very beginning, and that value itself is already sorted because that's the only value. So we started the first expansion to include the value on the index 2. Okay, and then what we are going to do is, well, we are going to put the I into the key, and then for this part from the 3 to 6, we are shifting the values to make the space for the right value to insert. So the value we are inserting is a key. Okay, and then eventually we want to insert the key to the right place. Okay, so for this algorithm, what is the precondition of this for loop? For the precondition, we should have a list ready, and all the values should be comparable. If we have the strings here, if we have a nested list here, and it will screw everything up. So we are assuming that we just have a normal array of values and a comparable values, right? And then what else? Are we doing a zero-based indexing or one-based indexing? We have done one-based indexing. Remember, this is not just for this insertion algorithm, this is for the whole textbook. Okay, and then, okay, let's check this one. How many times will this loop execute? That's a hard question. So remember, for the inner loop, for line 4 to line 6, what we do is we want to shift the values from one side to the other side so that we make the right place to insert the new value. So in the best case, well, we just do one check and then we don't do any value shifting. So in this case, well, line 4 will be executed once because we are doing this check. We check this condition and then we will say, okay, this condition is not true, but still we check this condition once. That is for the best case. So for the best case, for each time we reach the line 4, we check it once and then we are done. Okay, and how about the worst case? So for the worst case, say if you got 3, and then you have 5, and then you have 6, okay? And eventually, when you are inserting 1, what is going to happen? So you have to shift 6, and then shift 5, and then you shift 3. So after all those 3 values are shifted, now you have the space to insert the 1. So how many values are you going to do? So this is to insert the 4th value. To insert the 4th value, in the worst case, you have to do 3 shifts, right? So that is I'm just using those the 4th value as example. Say in the best case, when we are inserting the 4th value, or when we are expanding the sorted portion to include the 4th value, and then we only do one check, so we execute the line 4 once. That's the best case. And what's the worst case? The worst case is if when we are expanding to the 4th value, and then we have to shift all 3 values. So we have to run this line of code for 4 times, because 3 times we do the shift, and the number 4 we reset again, and then the condition is no longer true, and then we stop. But there are a total of 4 times. Okay, and well, and then I think this video is long enough. I want to stop the video here, and I will continue in the next video. And in the next video, we are gonna go through the running process of the insertion sort again. Okay.